currently, I'm a senior research scientist at Agency Science Technology and Research in Singapore. So today, I'm very glad to present our research paper, Large Language Model for Intent-Driven Session Recommendation. So session recommendation is one of the most important research topics in the area of recommender systems. And typically, in different sessions, the users may interact with multiple items, and these items may reveal diverse user intents. So for example, as shown in the figure, so the user behaviors in session 1 involves one intent, that is a laptop and accessory, while the user behaviors in session 2 reflect two intents. One is a laptop protector, and the other is a camera accessories. So therefore, many session-aware recommendation approach has been proposed to capture the diverse user intents for improved accuracy. However, this method suffers from several limitations. So for instance, they make an impractical assumption that all the sessions have a uniform and fixed number of intents. And most importantly, most of the algorithms can only infer the implicit user intents in the latent space. So therefore, to address these challenges, we propose an intent-driven session recommendation approach by leveraging the self-reflection ability of large language models. So our proposed methods mainly consists of three components. So first of all, the prompt initialization module aims to create an initial prompt to infer the varied user intents at a semantic level, and then the prompt optimization module aims to automatically optimize the initial prompt with an iterative self-reflection. And lastly, the prompt selection module is used to select the optimize the prompt across diverse domain. So here is a figure for the overall framework of our proposed methods. So first of all, we'll create an initial prompt as shown in the prompt 1-8. So maybe the font size is a little bit small, sorry. Yeah, maybe you can refer to the figures for the detailed prompts. Okay, so this initial prompt is mainly used to get the large language model in understanding the varying user intents at the semantic level for the next item prediction based on the user's historical session. And these sessions are fed into large language model by using the prompt 1-B. Okay, and then the recommendation list generated by the large language model is evaluated based on the ground truth items to collect the error case. So here the error case refers to the ground truth item ranks at the bottom half of the recommendation list. So that is to see the current prompt is not able to accurately make the recommendation. So in this case, we leverage the self-reflection ability of the large language model to infer the reasons behind. So by using prompt 2, we infer the reasons, and then given the inferred reasons, we ask the large language model to improve the previous prompt to make more accurate recommendation by using prompt 3. So here is the prompt 3. Okay, and then after that, so the prompt 4 is an example of the refined prompts. And to obtain more effective prompts, so we further augment the refined prompt by maintaining a same semantics. So prompt 6 is an example of the augmented prompts. So let's say if we have n numbers of error cases in this batch, so at this step, then we will have 2 times n numbers of improved prompt, including the augmented one and the refined one. And then next, our goal is to identify the most effective prompts to make the more accurate recommendation. But it is not impractical to evaluate all of the prompts by using all the training samples. So therefore, to improve the efficiency, we adopted the upper confidence bound bandits, the UCB bandits, to estimate the performance of all the prompts based on randomly sampled batch of training samples. And then the prompts with a higher reward value will be selected. And then these top prompts top-ranked prompts will be used to update the prompts in the previous iteration. So this process will iterate several epochs. And also in our experiments, we find that although the top one prompt, so for most of the training samples, it can help achieve the best recommendation performance. However, for some of the training examples, maybe the top 2 or top 3 prompts will have achieved the best performance. So to maximize the accuracy improvements and inspired by the generalization ability of large language model, we further investigate the cross-domain performance of the optimized prompt. And interestingly, we find that the prompt optimized in the domain with shorter and smarter sessions achieves the best performance across all domains. So in our study, we consider 3 domains: the movie lens, the Amazon video games, and another bundle set, which is also about the Amazon data set, but it involves domains like electronic, clothing. So these data sets were released by our previous SIGIR paper in 2022. Okay? And then the prompt optimized in such a domain will be selected as a final optimized prompt. Okay? So this page shows the algorithms. So the left one shows the UCB bandits. So the key idea behind is that the UCB bandit will sample a prompt based on their estimated performance. So gamma here is the exploitation coefficient of parameters. And then the performance will be evaluated based on the recommendation measurements. Here we adopt NDCG, and then their estimated performance will be updated by the observed preference. And the algorithm 2 shows the overall flow of our proposed approach, including collect error case, infer readings, refine and augment prompts, evaluate prompts by using the UCB bandits, and finally update the prompts with the top prompts. And this process will be done iteratively. Okay. And next, during the inference stage, given the user session, which consists multiple items, as well as the optimized prompt, so we feed them into the large language models, then we'll be able to get the response and recommendation. So in our case, there are 2 intents identified. The first one is popcorn-related intents, and the second one is the coffee-related items. So based on these identified intents, the recommendation list is generated. Okay. And regarding the evaluation, we adopt 3 data sets. The first one is the mobile lens data set. The second one is Amazon video games. And the last one is the bundle data set, as I mentioned. So this data set was released in our previous SIGIR papers. And to construct this data set, we conduct carefully designed cross-sourcing tasks to ask the workers to label the bundles as well as the intents in each session. And we adopted the key ratio and NDCG to evaluate the accuracy of the recommendation performance. And we compared 5 types of baselines ranging from the traditional one and the session-aware recommendation, which can either capture the single intent or multiple user intents. And because our prompt selection is based on the cross-domain performance, so we also compare the baseline in the area of cross-domain recommendation. And the last one is the large language model-based baseline. Okay, and so here the table shows the performance comparison of all methods across the 3 data sets. So from the results, we can observe, first of all, our proposed method outperforms the runner-up with more than 15% regarding to the accuracy metrics. And we also conducted the application study to verify the efficacy of each modulus of our proposed methods. And meanwhile, we also test the generalizability of our proposed methods So consistently, the prompt optimized in the game domain performs the best across all the domains. So, okay, and so next we also investigate the impact of different initial prompts. So in our experiments, we are using prompt 1-A as the initial prompt. And also we do some changes to obtain more diverse initial prompts to investigate their impacts. So compare with prompt 1-A. So prompt 1-C change the keywords combination of items as item groups. And regarding prompt 1-D, so we simplify the full subtasks in prompt 1-A to prompt 1- to the two subtasks in prompt 1-D. Okay, and here the table shows the results. So from the table, we can see that the performance of the optimized prompt will be affected by the quality of the initial prompt. And secondly, we notice that the streamlined description and subtask division can enhance the quality of the initial prompts. So for example, the prompt 1-A is more complicated than prompt 1-D. However, the optimized prompt based on 1-A performs worse than the prompt optimized based on 1-D. And thirdly, we find that the lower quality initial prompts are more likely to achieve more significant improvements. So as we can see that, so the first line shows the performance of the initial prompt, and the second line shows the optimized prompt. So this is for prompt 1-A, 1-C, 1-D. So from the table, we can see that the lowest quality is prompt 1-C, but it achieves the most significant improvements across the accuracy metrics. And we also study the impacts of the ground truth. And to achieve this, so we provide the ground truth item in the inferring reasons step. So that means when we're asking large language model to infer the reasons identified in the errors, we directly tell large language model, okay, the ground truth item is blah, 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 and please infer the reasons. But from our experiments, we find that directly tell large language model the ground truth cannot improve the performance. And meanwhile, we also investigate the impacts of the batch size. And lastly, let me talk about the limitations of our proposed methods. So despite the effectiveness, so our model also suffers from several limitations due to the inherent issue of the large language model. So for instance, it may generate hallucinations for some fashions. So for example, the response does not included in the ranking list, or the ground truth item is not included in the ranking list. So here the table shows the percentage of the sessions with hallucination. So these are the 3 prompts optimized in the 3 domains, and these are the 3 data sets. So overall, there are around 5% of sessions with hallucination issue. On the other hand, it also indicates the rooms for our algorithms to further improve the performance if this hallucination issue can be properly handled. And actually, to improve the situation, we also try to use the JSON mode in the response to control the output. However, we empirically find that using the JSON mode can marginally reduce the hallucination issue, but it may significantly sacrifice the accuracy. So let me quickly wrap up my presentation. So in our study, we introduced a new paradigm for intent-aware session recommendation by leveraging the self-reflection ability of large language model and being equipped with 3 modelers: the prompt initialization, optimization, and selection. So our proposed method is able to identify varying user intents at the semantic level, and the experimental results on multiple real-world datasets verify the effectiveness of proposed methods. and meanwhile, we'll also discuss the limitations of our proposed methods. Okay, thank you for your attention. So I'm happy to take any questions. Thank you.